Yeah, excellent. Right. I think this is our last, my last session with you. Okay. Isn't it? Yeah, this is my last session with you. So what I would like to do today is cover frames. Okay, we did beams, right? And we are going to look at frames now using moment distribution. In terms of the analysis itself, frames or frames, beams are exactly the same. There is absolutely nothing new whatsoever. Okay, so we're just going to use the same steps that we've used for analyzing beams to analyze frames. And I'm going to try and do two examples today. Hopefully we have the time to do two examples. So bending moment, moment distribution method for frames. Okay. The only thing I would like to the only thing I would like to say here is that the frames we are going to analyze are non-sway, because if you have a frame, let's say I take this frame here, for example, and I've got some loading. Let's say this frame is going to sway when you apply load. Do you agree? Yes. So we have a sway lateral movement. Okay, here we have a sway frame. Okay, if I take the same frame here and I restrain it, okay, so I put a restraint there, then obviously it becomes a non-sway frame. Okay, what I'm saying is we are not covering these frames, we are covering this here. The reason is it takes longer. That's all. It takes longer to analyze frames, non-sway frames using moment distribution, because you have to do it in two stages. Because you've got a displacement here that you need to take into account. Okay. So the moment distribution method in this case is you have to do it in two stages. You have to do two tables. It's very long, quite lengthy. So we're not going to cover, we haven't got the time to cover that. I would love to, but we haven't got the time. So I'm going to focus on non-sway frames where the lateral movement is prevented. Is that clear? Okay, so the first example 1. Okay, example 1, we've got this frame here. And so it's fixed there, and it carries a load of 100 kilonewtons, and we have A, B, C. The column height is 4 meters, and the beam in this direction we have got 2 meters and 2 meters. The rigidities are given, so we have, for AB we have EI, and for BC we have 2 EI. So the first thing we are going to do is, what's the first step? Just like moment distribution. Yeah, fix it. Look, the way you can think of this, the reason I've said the analysis is exactly the same, this is equivalent as if you had a continuous beam like this. So you substitute B here by support. Yeah, and so we have A, B, C. Is that clear? The analysis is identical. It's exactly the same. If I give you this beam or this frame to analyze, the steps, the analysis is exactly the same. The only difference will be when we get later on to the bending moment diagram, okay? Where you need to to know how to do it. But otherwise, in terms of the analysis, you can think of this column as if you had a beam without any loading, and then for BC you have got this beam here with the point load in the middle. Is that clear? So the steps we're going to follow are just the same. Okay, so number one, fixed end moments. So fixed end moments for AB. Okay, for AB we have got this. And these are the fixed moments. So what can we say about the fixed moments? What do you think at A and B? Yeah, there is no loading. So AB is not loaded. So FEM AB is equal to 0, and FEM BA is equal to 0. Okay? AB not loaded. Okay? There is no loading at B. On AB, so therefore the fixed moments are 0. Okay, then we do the same for BC. This is BC here, and this time we have a concentrated load in the middle, and the span is it's in the middle, and the length is 8 meters. 4 meters. And these are the fixed moments, okay, B and C. So we have FEM BC is minus, what's the equation? WL over? Yeah, if you don't know it, don't worry. You'll be given the table in the exam, so you don't have to memorize them. But if you do know them, it's good, okay? So it's WL over 8. So we have minus 100 times 4 over 8, which I think is 50. I don't know. Is it 50? Yeah. Kilonewton meters. And the same for CB, sorry, except that it's with the plus sign. So we have plus 50. Yeah, so that's easy, first step. Yeah. Second step, we determine now what's the next step? Distribution factors. So now the DFs, now the distribution factors. We have 3 joints, joint A, joint B, joint C. So we do it for each of the joints. Joint A, there is only one member connected to A, and obviously there is a solid foundation here, so it's very rigid. And at C, imagine you have got a wall here, which is infinitely rigid, okay? So therefore, so we have A, B, and C, okay? We have 3 joints. So what is it for joint A? We have only one member connected to A, and that's member AB. So what's the distribution factors if it's rigid? Yeah, exactly, always. And then at B, we have 2 members. We have member BA, and we have member BC. Okay, for member BA, stiffness of BA, which is 1. Okay, look here, as if we had a 1. Can you see we have EI? This is as if you have 1 EI, and this is as if you have 2 EI. Is that clear? So we have 1 over 4 and 2 over 4. You got that? Yeah, so it's 1 over the length 4 and 2 over the length 4 when you do that, okay? So we have stiffness of BA, which is 1 over 4, divided by stiffness of BA, 1 over 4, plus stiffness of BC, 2 over 4. And that's it. And I believe this is third, isn't it? It's the length. 1 over the length of the member, 2 over the length of the member. Is that okay? Yeah. So that gives a third. I mean, the EI will cancel, so you don't have to write EI 1, 1 EI, 2 EI, etc. Because the EI will just cancel, okay? So you can just put the coefficients here, 2 and 1, and forget about the EI. Is that okay? Yeah. So that gives 1/3. And for BC, we have stiffness of BC 2 over 4 over stiffness of BA plus stiffness of BC. And this time is 2/3. Okay? And you can see that the sum is 1. the sum is equal to 1. Similarly, for BC, for joint C, we have only one member at joint C, and that's member CB, and it's going to be equal to 0 because there is only one member and the joint is rigid. Is that okay? Yeah. That's it. We've got everything now. We have everything we need to construct that table. Okay? It's very, very straightforward, as you can see, right? So you can do it for a frame just like you do it for a beam. Okay? So next step, moment distribution table. Moment distribution table. Is it clear? Any questions? Anyone? Any questions? Okay, thank you. So let's do the table. You always need 4 rows to start with, okay? So 1, 2, 3, 4, okay? Leave some space. You may need about, maybe half a page. So we have the joints in the first row. In the second row, we have the members connected to the joints. On the third row, we have the distribution factors. And finally, on the fourth row, we have the fixed end moments, We have 3 joints. We have joint A, we have joint B, we have joint C. Joint A, there is one member connected to joint A, and that's member AB. Okay, so you have one member connected to A, and that's member AB. For joint C, B, we have 2 members, BA and BC. Okay, so we have BA and BC. And finally, joint C, we have only one member, and that's member CB. Then we write down here the distribution factors as obtained. So for AB, we have 1. For BA, we have 1/3. For BC, we have 2/3. And finally, for CB, we have, was it 0 here? Sorry. Okay. Now, fixed moments, we have AB 0, BA 0, BC minus 50, and CB plus 50. Okay, now we have one intermediate joint. We have one intermediate joint, this one here. These are end supports. So we have one intermediate joint, and this is where we are going to balance and then carry over to the adjacent joints. Is that clear? Right? So here you have, this is joint B, okay? This is joint B, and you can see that we have an outer balance here of minus 50. Okay? So, and that means we have a balancing moment of how much? The balancing moment is the opposite, yeah, plus 50. So in other words, this is how much we need. So we have plus 50 times 1/3. What is 50 times 1/3? I mean, you can leave it as a fraction, I don't mind. I've got 16.67 plus. Okay, so this is balancing, and this is balancing here. And we have, please check them, 33.33. Yes? Okay, so do we carry over to A and C? Yes. Yes, because they are fixed. So we carry over half from B to A. We carry over half, which is 834. And we carry over half from joint B to joint C, and that is 16 point, is it 69? 67. And because we've got only one intermediate joint, what happens is, after one iteration like here, you find that the equilibrium will be satisfied, okay? So we draw a line here, so this is balance, and this is here carry over. And then we draw a line to get the final final moments. So we have 0 plus 834 is 834. 0 plus 1667 is 1667 with a plus. And minus 50 plus 33, please do check it, is minus 1667. And then you have plus 50 plus 1667 is 6667. So, okay, yeah. So what do you notice here? The joint B now is balanced. So we have equilibrium. That's it. So we have achieved the objective. Okay. So now the joint is balanced. Joint B now is balanced, and therefore these are the final bending moments. Any questions on the table itself, please? Okay. So let's take the beam itself. The frame. So this is the frame. We have AB here, and we have BC. Okay, so this is the frame. So we have A, B, C. Okay, at A, we have plus. So that's clockwise. So we have clockwise 834. So we have clockwise. Okay, clockwise 834. At B. On BA we have clockwise because it's positive, so clockwise here 1667. Then we have at B again, we have anti-clockwise 16.67, and finally at C we have plus clockwise 66.67. Is it clear? Yeah, so you look at the sign here, and the sign will tell you whether it's clockwise or anti-clockwise, and you just apply it there. Is that clear? Any questions? Anyone, any questions? Okay, now we can use that to plot the bending moment diagram, and to do that correctly, in order to plot the bending moment diagram correctly, remember what we said, what did we say last week? Or not last week, last Tuesday. What did we say? Do you remember? Yeah, but which side do we plot? On the tension, exactly. So what you do, you look at A here. You can see where is the tension. Is the tension on the left or is it on the right side? Yeah. Do you agree? It's on the right here. Yes. Yeah. This is the column. Okay, this is the column, and you can see the bending moment is going this way. Yes, if it's going this way, can you see that it makes this side in tension? Agreed, everyone? Yeah. Okay. At the top, we've got this moment this way. Yeah, this way. So the tension is on this side. You see that? At the top, the tension is on this side here. And then top and top there, okay? And these are the tension, the sides where the tension occurs. I mean, this way you plot it correctly. You draw your bending moment correctly, because if you don't follow this, you will have your bending moment diagram all over the place. So you have this plotted maybe on this side and this on this side, and it doesn't look right at all. You have to follow a convention that you apply consistently. To make sure you have got the correct bending moment. Don't forget that we have got a point load there in the middle. Yeah. So now I can do it here in this diagram there, next to it. So we have 834 on this side. we have 16, 67 on this side. We have at the top there, at the top we have 16, 67, and at the top here we have, I'm not drawing to scale, we have 66.67, and don't forget, as I said, that we have a point load there, so therefore now you join the points together. And that's the bending moment diagram for the frame. Is that okay? Yeah. So you plot your values on the side where there is tension. Okay, so you plot your values on the side where there is tension. Top, 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 okay? And then you join together. Because you've got a point load there in the middle, so your bending moment diagram is linear. Okay? If we had the UDL, uniformly distributed load, it would be parabolic. Is that clear? Okay? So that's the bending moment diagram. The only thing we need to determine here, that, are these points of contraflexion, this here, and the maximum bending moment there. Okay? So we have 2 points of contraflexion for BC, and we have 1 point of contraflexion to determine for member AB. So we need to determine this point. Let's call this D0. Let's call this here D1, and let's call this here D2, okay? And we need this bending moment diagram, maximum moment as well. Okay, any questions? Right? Yes.
When B, where we have 1667, should be tension on top?
Sorry?
On point B, where the moment is 1667. Yeah, minus 1667, top one.
Yes?
The tension should be...
Should be at the top?
Yeah, well, yeah.
Yes, so you plot it at the top. You've got this. So the tension is at the top, okay? Yeah, the moment is anti-clockwise, and the tension is at the top. So you plot the value at the top there of the member. Okay? That's your member, and the 6067 is at the top. Okay? Right, so let's determine the distribution, the point of contraflexion here. How can we determine the point of contraflexion, the location? There are 2 ways. Either you take this member here, turn it around, determine the reaction forces, and you then determine the distribution factor, point of contraflexion. Or what's the other way? Do you know similar triangles? Have you heard of similar triangles? Yes? So if let's take this member here. Can you see this member? AB. So member AB, let's start with AB, okay? I show you what I mean by similar triangles. See, if I extend this line here, parallel to this, yeah? So this is what this is the D1 if you want. This is D0 here. What is this length? Sorry? 4, you agree? What is this length? Yeah, the unknown, we don't know it, yeah. Can you see this triangle here, the big one there? Can you see that? And this smaller one here, can you see it? These are similar triangles. This triangle here, I repeat, this triangle, okay, is similar to this triangle. It's just smaller. Yeah, because these two lines are parallel. So you have the big triangle there is similar to the triangle there. This is what we mean by similar triangles. Similar triangles means they are the same, except that one is smaller than the other. So you have the lines are parallel. So that's a good example. So you have this line, this one, and this one there are similar. Okay. So if these two triangles are similar, then we have got this side. Look there. Divided by this is equal to this divided by this. You agree? Okay, so you've got this one divided by this is equal to this divided by this. Because they are similar triangles. Is that clear? It's just a smaller size, okay? So we have, what's this side, what's this here? Can you tell me what's this there? Do you agree it's 4 minus D0? Do you agree? Yeah. Divided, what's this here? Exactly, because it's there. 16.67 equals, what's the height here is 4 divided by, what's this there? Exactly, together. You agree? So 16.67 plus 8.34. And that's it. And we have got one unknown in this equation that we need now to resolve. So basically, you solve by multiplying across there, isn't it? That's the rules of the fractions. So we've got 4 minus D0 times 16.67, plus 8.34 is equal to 4 times 16.67. What's this 16.67 plus 8.34? Yeah, I've got it there. Thank you very much. And 14 times 16.67. If you've got a calculator, you can skip all this and do it in your calculator. I'm just trying to do it manually. So can you work this out, please, and give me D0?
1.3.
Sorry?
1.3.
1.3.
1.3.
Yes? Yeah, to one decimal place. Do you agree, everyone? Please do check it. And that's exactly what I have when I did it earlier, okay? 1.3. Yeah. I mean, the other way will be to determine the reaction forces, okay? And do it as we did last week. But in this case, because it's a linear, because we have the geometry is linear, you can always use similar triangles. You use geometry, okay? The only problem, if you have a parabolic distribution, obviously you have to do it the hard way by determining the reactions and then taking the cut, okay? Any questions, please? Is that okay? Yeah. Let's do now member BC. Please stop me if there are any questions at all. Just stop me. Online students, I can hear you. So if you have got any questions, just shout, please. Okay. So member BC, can we do BC now? Yes. This is BC. If you look at BC, if you look at member BC, if I can explain this here, you cannot, you could use similar triangles because for this side and this side, but we don't know the this value here. Okay, so the first thing we need to do is to determine the bending moment at the, as if I call this here D, we need to determine the bending moment at D, and then we can use similar triangles if we want. Okay, so let's call this point here point D. In order to find the bending moment at D, what do we need to do? First thing. Reactions, isn't it? So we have a reaction at B, VBC, and we have a reaction at C, VCB. The span is 2 meters and 2 meters. So first of all, let's take moments about, you can start about B or C, it doesn't matter. So let's start about C, for example. So we take a moment about C. Clockwise, we have VBC times 4. And then clockwise, we have 66.67. And then equals, anti-clockwise about C, we have 100 times 2 and 1667. If you have a calculator, please, if you can check this for me. Please do it yourself, and just to make sure you know how to do it. I've got 37.5, if you want to check it, please. Yeah, is that what you got? Yeah. Yes, thank you. And then we do the same. We take moments about B. So let's take moments about B. Again, clockwise moments equal to anti-clockwise moments. So you take anything clockwise about B equals to anything anti-clockwise. So we have B here. Clockwise, I have 100 times 2. Clockwise, 66.7. I think that's everything clockwise. Then anti-clockwise, I have C VCB times 4 plus 1667. And again, please do check it. I've got VCB 62.5 kilonewtons to 1 decimal place. You got that? Is that what you get as well? Yeah. How do I know if I'm right? The sum is 100. Yeah. So always do 2 moment equations. Always. So check. VBC plus VCB is 37.5 plus 62.5 equals 100, and that is equal to the 100 applied load, and therefore it's definitely correct. Okay. So you've got the sum of the reactions there equals to the external load, 100. Okay? Any questions? Okay. Shall we do the, now we need to get the distribution, sorry, the points of contraflexion, right? We have two, now we know the moment at D, we know it, it's, we know the reactions, so I can determine the moment at D, we can do that. What's the moment at D? Look there. You can calculate the moment at D from the left or from the left, from the right. I can guarantee you get exactly the same answer. All right, so you can do it from this side or from this side, which way you want. Shall we do it from the left? Okay, so from the left we have VBC. We know VBC now. VBC is 37.5 and VCB 62.5. So we have 37.5 times 2 and then minus 1667. I've got 58.3. Can you check it, please? Is that correct? Thank you very much. And ask a question for you. Can you, using your calculator, can you work out MD from the right, please? Just see if you can do it. See if you can get the same 58.3. Calculate MD from the right side. Yeah, so you do VCB times 2 minus 66.67. Agreed? Yeah, so that's another way of checking your answers, okay? Everything is linked together, right? Is that okay? Right, so we've got MD, now we know the bending moment at D. I can now use I can use similar triangles for the left side, and then I can use similar triangles for the right side here to determine D1 and D2. The other way I could do is taking cuts. Which way you prefer, geometry or taking a cut? Geometry?
Is geometry the similar triangle?
Yes, it will be the same. The only thing you need to remember, we are going to do an example in a minute. If you have a UDL, obviously you can't use similar triangles. That's the only thing. So I think it would be better if you know how to do it using cuts, because you can use it for any situation. Okay, but let's do the similar triangles here. So so this is the BC. We have 66, 67. We have 58.3, and we have 1667 there. So what I'm going to do, I'm just using these dotted lines just to guide me to show you the triangles in question. Is that okay? This is D1. This is here D2, okay? This is 2 meters, and this is 2 meters. Is that clear? Yeah, so you can see now with the dotted lines, you can see the triangle, the similar triangles on the left, there, these 2 triangles here, okay? And you can see these 2 similar triangles here on the right. Is that clear? So we are now focusing on the first one. Let's do the first one. So I have, so I do it here. So I have 1667 over D1 is equal to 1667 plus 58.3 over 2. Okay? And then on the right here, I have 66.67 over D2 is equal to 66.67 plus 58.3 over 2. And that's it. So you get, if you get me D1 from this side, please, and you get me D2 from this side. Sorry? Yeah, I've got 0.45. Sorry? Yeah. So roughly 0.45 meters. And I think I've got D2, I've got 1.07, if you can check it. Yeah, thank you. 1.07 meters. Both of them, D1 from, this is from B, and this one is from C. Is that okay? Yeah? Any questions? Anything at all? Anything whatsoever, please? Anything at all? Anything not clear? Sure. Okay. I mean, I can now, I can complete it by drawing the fully annotated bending moment diagram with all showing all the values. And that's the fully annotated bending moment diagram for the frame, showing all the maximum values and the points of contraflexion. Any questions? Doesn't matter. I mean, if you want to show the plus minus, there is a convention. You have to be careful. You use, do you remember what I said last week about smiling face, sad face? Yeah, I mean, yeah, exactly. If you want to put the signs on the diagram itself, don't put the signs that you've got here in the table. You put the signs in relation to sagging and hogging. Okay, so that would be your, that would be sagging, that would be minus, that would be minus. Okay, and yeah, okay. But I don't ask you to do it. You don't have to do that. Okay, but if you don't want to do it, that's fine. Yes.
The vertical one, or is there not?
No, there is, because that will be minus, okay? You look at it this way. Imagine you've got your eye here, okay? So you've got this one hogging and this one sagging. Okay? But as I said, It's not really important, because even if you are designing in practice, if you design the column, you take the maximum value of the moment anyway, regardless of the sign, because that's how you design it, yeah? So if I have 1667 and A34 for this column, I will design it for a moment of 16.67, okay? Any questions? We have, it's spot on 11:50. Do you want a 10-minute break? So we'll have a 10-minute break, then we have another hour to do the next question, which is very, very important, okay? And then we finish, right? So 10 minutes. Okay, I think we need to start. So let me get the second example. So example number 2. So doing now the second example, okay? Is everyone back or no? Okay, example number 2. So we have got a frame as well. This time, the frame is fixed at this end and pinned at this end here. So we have a pin at this end. So we have A, B, C. BC carries a uniformly distributed load. So we have a UDL here of 5 kilonewtons per meter. Okay, and AB carries a point load in the middle at mid-span. So we have 20. Okay, so we have 20 kilonewtons, and the span is 2 meters. And this span, BC, is 3 meters. If you want, this is equivalent as if you had a continuous beam like this. Yeah. So imagine you have a continuous beam like this. That's exactly, in terms of analysis, that's the same. Is that clear? Yeah. Okay, so step number 1, fixed moments, same as usual, okay? You've got your table. What you need to be careful here that the end here at A is simply supported. There's a pin, basically, okay? So when you use the table, pay attention to that, okay? So number 1, distribution, fixed moment, sorry. Yeah, given we have got 2 EI and we've got 1.5 EI. Oh, okay. Can you see now? You can now. Okay, thank you. Thank you. Sorry about that. Okay, thank you. So that's the example, because they were not able to see the online. So that's the example you have. Okay, we have a ported frame, ABC, right? It's simply supported at A, and it's fixed at C. It carries a UDL of 5 kilonewton per meter for BC, and then it carries a point load at mid-span on AB, and the rigidities, the flexion rigidities are given, 2 EI for AB and 1.5 EI for BC. The span for AB is 4 meters, and the span for BC is 3 meters. I was saying that in terms of the analysis, this is equivalent to analyzing this beam here. Okay, so the first step is to determine the distribution, the fixed moments using the table. You don't have to memorize them. I know them by heart because I've used them so many times. But in your case, the table will be given, so you don't have really to memorize them. Okay. So fixed moments. Let's start with AB. So AB, we have got this. So when you split it up, so you've got a AB, okay? And this is the fixed moment for AB. Is that okay? So what does it, so what's the fixed moment at A?
0.
Yeah. So FEMAB is 0. FEMBA? Look at the table.
Minus 3WL over 16.
Okay, what does it say on the table? It says minus, isn't it? But can you see that that figure on the table is actually flipped horizontally? Yeah. So what's the sign of the moment here? Plus, exactly. So be careful. Yeah, what you have on the table there is actually the same figure, but actually flipped horizontally. Is that okay? So we have got here plus 3WL over 16, which is plus 320 times 4 over 16. I've got 15. Yeah, thank you. Plus 15 kilonewton meters. Okay. Yeah. So let's do now BC. That's member BC, fixed, UDL, W, 5 kilonewton per meter, and the span L is 3 meters. And these are the fixed moments at B and at C. So we have FEM BC. I think Joseph is... you still cannot see. Can you see now? Can you see it now? Can you see the screen now? Blank. You can see it now, okay? Okay. So, so fixed moments at B, we have minus, what is it? Minus W square over 12. Have you got your table? Yep. So minus W square over 12. So we have minus W 5, S squared, 3 squared over 12. I've got 375. Minus 3.75. And at B, it will be exactly this. At C, sorry, it will be the same with the plus. So 3.75 kilonewton meters. Is that okay? So we've done the first step. That's good. So let's do the distribution factors now. DF's distribution factors. Distribution factors. So we have AB and BC. So we have 3 joints. We have joint A, joint B, joint C. Okay? Joint A, we have 1 member connected to joint A, so we have DFAB. Do you remember what's the distribution factor? Yes. Okay? If it's fixed, it's 0. If it's simply supported or a roller, it's 1. We did show it last time, okay? Because it's the member divided by itself. So you get 1, okay? So we have 1 here, okay? Pinned support. Okay? Then we have got 2 values. For B, we have member BA and we have member BC. Member BA, okay, now this is where you need to pay attention again. Member BA, we have stiffness of BA. What is the stiffness for BA? Look, do you remember what we said last week? Because this end is not fixed, it's pinned, so the rigidity will be reduced, isn't it? Yeah, by a quarter, so it's not 0.75, okay? So it's not 0.75. 2 over 4. Yeah, so you need to pay attention, please, when you have a pin like this at the end, okay? So it's not 0.75, 2 here over the length of the member. Is that clear? It should be like 2 EI over 4, but the EIs will cancel, as we said, okay? So you don't have to. And then divided by stiffness of BA plus stiffness of BC. So it's not 0.75, 2 over 4, plus stiffness of BC, which is 1.5 over 3. So you need to multiply the stiffness of AB by 0.75. Can you check the answers for me, please? I got 0.43. Yes? Okay, thank you. Okay. So now we do the same for BC. So it will be stiffness of BC, which is 1.5 over 3 divided by 1.5 over 3 plus 0.75, 2 over 4. And again, if you can check this for me, please, I got 0.57. Thank you. And the good thing is the sum is 1, so that's good. So it gives us some satisfaction that the answer is right. Okay, so, and then finally for C, so DFCB, what is the fixed moment? Sorry, the distribution here? 0, because it's fixed support. That's it. So we've got everything now, again, for the table. So there are a few things here where you need to pay attention, okay? One is the fixed moments here, and the fact that this figure is flipped horizontally, and then you need to multiply the distribution, the rigidity here, the flexure rigidity, by 0.75. These are really the main things to pay attention to. The rest is exactly the same now, okay, from this point onwards. Is that okay? Okay. So, table. So, moment distribution table. Now the moment distribution table. So again, leave about half a page. Joints, members, fixed distribution factors, and fixed end moments, okay? We have joint A, we have joint B, which has 2 members, and finally we have joint CA there, okay? We have AB, BA, BC, and CB. For distribution factors, we've got at A we have 1, for BA we have 0.43, for BC we have 0.57, for CB we have 0, and fixed moments we have 0, plus 15, minus 3.75, and plus 3.75. So we have an out of balance here. If you do 15 minus 375, I think it's 11.25. Yeah. In other words, the balancing moment is actually minus 11.25. This is how much you need to balance. So I'm going to multiply this balancing moment by the fixed and the distribution factors. So we have 11.25 minus times 0.43. So you multiply this balancing moment by 0.43, which gives minus 4.84. Then you do minus 11.25 times 0.57. It's minus 66.41. Okay, now we need to carry over, isn't it? So that's balanced. So we have balanced now, and then you carry over. Now remember here. Can we have silence at the back, please? So because A is pinned there, you do not carry over from B to A. There is no carry over from B to A because A is pinned. It doesn't have a moment. There is no moment at A. So there is no carry over from this end from B to A. Is that clear? But you carry over half from B to C. You carry over from B to C. You do not carry over from B to A. Clear? So that's another difference, okay? So 641 divided by 2 is minus 3.21. And draw a line, and it should be balanced out, okay? So we have 0 at A. So these are the final moments. We have 0 at A. We have plus 15 minus 484 is 1016, I believe. And minus 375 minus 641 is, please do check it, is minus 1016. Then we have 375 minus 321 is plus 0.54. It's a very small moment that we have at C. Nevertheless, we do have a moment at C. It's because of the choice of the UDL. If I've chosen a large UDL, you'll have a large moment here. Okay, so it's just pure coincidence. Is that okay? And now we have got the moments at B balanced. So they are in equilibrium. Any questions? Yeah? Okay. So let's look at the bending moment diagram. Have you got any questions on the table? Anyone? Any questions on the table? Okay, clear. Yeah. So that's the, this is the frame. Okay, we have zero, we have A, B, and C. Okay, so we have 0 at A, no moment at A. We have plus, we have positive 10, 16. We have minus, that's anti-clockwise, 10, 16. And finally at C, we have clockwise 0.54. And we've got 0 there. But don't forget, we have a uniform, we have a point load here on AB, and we have UDL on BC. If you want to show the tension, because you need it, so at B, at A, obviously there is no moment. At B, the tension is on this side. At B, on the beam, it's at the top, and the tension is at the top there. And that will help me. Now I can draw the bending moment diagram here. And that's the bending moment diagram, okay? We have a UDL, so it's parabolic, okay? And we have a point load here, concentrated load, so therefore it's linear. Okay, so we have 1 point of contraflexion here to determine, and we have 2 points of contraflexion, and these 2 moments to determine the maximum values, okay? So we have, if you want, we have 1, 2, 3, 4, 5 intermediate values to determine maximum moments and points of contraflexion. Any questions? Anything at all? Okay, so we need, so let's start with member BC. We have time, okay? So let's start with, let's start with AB. So intermediate values. Intermediate values. So starting with AB, let's start with AB. I'm going to flip this diagram horizontally. It's easier to see it, yeah? It's exactly the same. So let's take AB. This is AB. Okay, so this is AB. I have here. Okay, so that's the, we have got 0 there. We've got 10, 16. Okay, and we have got that point load in the middle, which is, what was it? 20, isn't it? Yeah, so we have 20 kilonewtons there, and the span is 2 and 2, so we have 2 and 2 meters. Obviously, this is A, this is B, so we have VAB, the reaction at A, and we have VBA to determine. Anyone, any questions? Clear. So we are going to determine these 2 reaction forces by taking moments about B and A. So let's start with B, for example. So moments about B, we have clockwise about B, we have VAB times 4 plus 10, 16, that's clockwise. Anti-clockwise about B, we have 20 times 2, that's it. I've got 746 for the reaction at A. Sorry?
Is it moments about C or moments about B?
We're talking about B here. Yeah?
Sorry.
Yeah? About B. It's a column that I flipped horizontally. It's easier to deal with it that way. Okay. So we have the reaction at A. Actually, I shouldn't even call them VAB and VBC. I should call them really HAB and HBC. These are horizontal reactions on the column, but it doesn't matter. They are reactions. So what do you get for the reaction at A, please? I got 746 as well. Thank you. So 746 kilonewtons. And similarly, if we take now moments about point A, we have clockwise about A, we have 10, 16. Clockwise, we have 20 times 2. And anti-clockwise, we have VBA times 4. And if you can check this again, I've got 1254 kilonewtons. You got that? Thank you. So how do I know if it's correct? Well, check. So we have VAB, the two reactions, VBA, are 746 plus 1254. If you add them up, I think it's 20, and this is equal to the 20 applied load. So therefore, it's correct. Let's call this point here point D, as before. So let's call this point here in the middle, let's call it point D. And I can do now, I mean, this is VAB 746, VBA is 1254. So I know the reactions now. So therefore, the moment at D will be 7. So MD will be 746. 7.46 times 2. That's it. There is nothing else. There is no moment at A, so it's 746 times 2. And that would be the moment at D. I've got 1492. Quickly, please, can you work out the moment at D from the left, from the right? See if you get exactly the same value, please, quickly. Can you work out the moment at D from the right? So it will be VBA 1254 times 2 minus 1016. 1254 times 2 minus 1016. Hopefully it should give you 1492. Yes? Good. Yeah, another check if you want. Okay. What else did we? Yeah, we said that we have got a point of contraflexion, isn't it here? So what is the point of contraflexion? The point of contraflexion is between these 2 points. Do you agree? So it's between D and B. So what I'm going to do, I'm going to take a cut between these 2 points here, right? So point of contraflexion is between D and B. The point of contraflexion is between D and B. I can take the origin at A or the origin at B. It doesn't matter at all. All right? It doesn't matter. Shall we take it from B? Yeah? So this is X here. So let's call this here X. Okay? Okay, so consider a cut at X from B. So consider a cut at X from B, and we have the moment. What is the moment at the cut here? Now, look. 12.54, yeah, times X, yeah. Yeah, that's it. And that's it, okay? So it's 12.54 times X, okay? You cover the right, you cover the left side. So it's 1254 times X minus 1060. That's the moment equation. If you want the point of contraflexion, that means the bending moment is 0, okay? So M equals 0. We have 1254 X minus 1016 equals 0. That means X will be 1016 over 1254, which gives, I've got 0.8. Yeah, is that correct? So it's 0.8 meters from B, So we've got 0.8 from B. So we've got the maximum moment at D, and we've got the points, the position of the point of contraflexion for this beam here. So this is 1492, and this is here 0.8. Okay, so we have defined the intermediate values for AB. Now we are going to do the same for BC. Is that clear? Okay, so we do it for BC. But for BC, obviously, we have got a parabola. We have a UDL, so it's parabolic. So therefore, we need to take a cut from B or from C, doesn't matter, and do and then work out the intermediate values. Okay, so now remember BC. So we finish with AB, we do now BC. So this is BC. I'm going to draw it here. We have 10, 16, 0.54, B and C, but we have a UDL W of 5 kilonewtons per meter. We have the reactions VBC, and we have a reaction VCB. Are there any, is anyone here doing 50-22, or we are all doing 15-21? The module, are you doing 50-21?
15-21.
Everyone here? Is anyone doing 50-22 at all? The BSc? No. Sorry? You are? I'll just say something about the exam in a minute, okay? I just want to finish this first. Okay, so let's do the reactions. Let's do the reactions. Take moments about B, or shall we do C first? Okay, moments about C. We have the span. We know, what was the span? Was it 3? 3 meters. So we have VBC times 3 clockwise plus 0.54, that's clockwise. Anti-clockwise we have 1016 plus we have the UDL, which is 5 times 3 times 1.5. Sorry, times 1.5. Okay, and I think, no, I think the answer I've got, if you can check it, please. I've got I've got 10.7 kilonewtons. Yeah, and then we take moments about B. We have clockwise about B, we have 0.54. We have the UDL, which is 5 times 3 times 1.5. Anything else clockwise? No. And then we have anti-clockwise. We have 1016 plus VCB times 3. Okay? And again, please check VCB. I've got 4.3 kilonewtons. Is that okay? So how do we know it's right? Well, we check. So we check VBA plus VBC is, not VBA, sorry, VBC. So we have 10.7 plus 4.3 is 15 kilonewtons, which is equal to 5 times 3. So therefore, it's correct, definitely. Okay? Yeah. If you check all your answers at every stage, the way I've done it, you will be absolutely 100% fine. Yep. But you need to know how to check your answers. at every stage. Then you can go only one step back and check, and rectify, rather than, finishing and then panicking. Is that okay? So always check your answers, please, at the intermediate stages. So we got now we do the intermediate values by taking a cut. So I'm going to take a cut here. Shall we take the origin at A? It doesn't matter. Okay, let's take the origin at B, sorry. So we have X there. So consider a cut, or section at X from B. So we consider a cut at the section from B. So we know the reactions. VBC is 10.7 and VCB is 4.3. Yeah, so you've got the reactions now. So what's the bending moment at the cut? 10.7 times X. Then you have got the 1016 minus 1016, but you also have the UDL, which is 5 times X times X over 2, the distance. Is that clear? Very straightforward. So we have M equals 10.7 times X minus 1016 minus 5 times X over 2. Which I can write as 5 over 2 here is 2.5, so I have minus 2.5 X squared plus 10.7 X minus 10.16. And that's the equation of the bending moment. Okay, this equation here gives you the bending moment anywhere along the span here. If you put X equals 0, you get 1016. If you put X equals 3, you get 0.54, guaranteed. Is that clear? Yeah. So while we are at it, so we've got M. So what's the shear? What's the shear equation? What did he say about the shear? The shear is you differentiate, isn't it? Yeah. So what's the shear? Can you differentiate this for me? Well, you multiply by the power, isn't it? So 2.5 times 2, 5, X, and then 10.7. That's it. 1016 when you differentiate 1016, it's a constant, so it's 0, obviously. Okay. So you've got minus 5X plus 10.7, and that's the equation of the shear. So to get which one shall we do first, maximum or point of contraflexion? It doesn't matter. Let's do the maximum value first. Let's do this one here. So M max corresponds to what? Shear 0. Yes, the shear is 0. So therefore, we have minus 5X plus 10.7 equal to 0. And therefore, you have X is 10.7 over 5. Okay, which I think is, sorry, 2.14, thank you, meters. And that's from B. Okay, from B. Now we can substitute back. We can substitute the X back into the equation of M. So M max. So therefore M max will be minus 2.5 times 214 squared plus 10.7 times 2.14 minus 10.16. We are substituting into the equation here X. I don't think I haven't got the answers from this point onwards because I haven't finished it earlier. So if I will be relying on your calculations here. So what is M max? 1.289. 289. Yeah. So 1.3 kilonewton meters. Thank you. Do you get the same answers? The others? Yeah, thank you. So we have M max is 1.3 kilonewton meters. Okay. For the points of contraflexion, we have we put M equal to 0. Yeah. So we have so we put M equal to 0. So we have 1 minus 2.5 x squared plus 10.7 x minus 1016 equals 0. And this is a quadratic equation, and the form is ax squared plus bx plus c equals 0, where a is minus 2.5, okay, a is minus 2.5, b is 10.7, and c is minus 10.16. And you calculate the delta, which is b squared minus 4ac, okay? And the first solution will be minus b minus square root of delta over 2a, and the second solution will be minus b plus square root of delta over 2a. If you give me the equation, if you give me the value for delta first, if you do b squared minus 4ac. You know, when you multiply a by c, you have minus by minus is a plus with the minus here, so it gives you a minus anyway. So it's 2.5 squared minus 4 times this 2 here, you know, a and c. What is delta? It will be a large number. Yeah, or if you directly on your calculator, it doesn't matter. As long as you give me the answers for x1 and x2.
X1 is 1.4.
1.4, yeah.
X2 is 2.8.
2.8.
2.86.
Yeah. Okay, and I can look at the diagram here, and I can see that the answers do make sense, because the value of the bending moment at C is so small that this point of contraflexion is so close to C. The span is 3 meters, and you've got 2.8. Can you see that? So that's perfectly, it does perfectly make sense, okay? And that's it. We have finished this example. So I'm going to plot the values here. So M max is, this is 1.3, this is 1.4, and this is 2.8. Okay, so the point of contraflexion 1.4 meters, 2.8, and the maximum moment there is 1.4 at 3 kilonewton meters. Is that okay? Yeah, we have finished this example. Okay. Any questions? Any questions? Yes.
How long would you give us to do all that in an exam scenario?
I'm going to cover the exam in just a minute. Have you finished all that, please? Yeah. Okay. Okay. All right. Okay. Thank you. Okay. for the exam, are there any questions, anything at all, please, before I say anything about the exam? Okay.